Now we will go into some more classical topics, though today I will show you how to view something from two different perspectives. From the perspective, I will give you a classic analytical proof, and then I will give you a proof using ergodic theory of what's called Weil equidistribution. It's the equidistribution of polynomial values modulo 1. So, the references here, well, for the analytic perspective, there are many references. I like the one that, well, so-called additive Davenport. It's a book by Davenport. What do I mean by additive Davenport? It doesn't have additive in the title, but it's a book by Davenport that is not called multiplicative number theory. So the colloquial name is additive Davenport. There are also notes by Tao and by other people, but for the ergodic perspective I will follow mostly Einsiedler and Ward, which is a very good book, because it really explains the ergodic and dynamical perspective to non-ergodicists. So at least for me it's very good. So why do we care about exponential sums? And what are exponential sums? Well, there are many reasons. One of them is that they are related to equidistribution, that is to equal distribution. Как это по-русски? Equidistribution? Равномерно. It's not quite the same as the uniform distribution. We will see. No, равномерно.
Not uniform.
I do not mean the uniform distribution, I mean something a bit different. I mean it when a sequence is equally distributed over an entire space.
As far as I know, it's something like равнораспределение.
Равнораспределение. Well, we will see. First of all, let us define what we mean by it. But what are exponential sums? So much of the work of an analytic number theorist is about finding cancellation. So usual work. Much of what we do in real life is things of this form. You have a sequence where each term is bounded, say, or almost bounded, say bounded by a constant, and we want to show that the sum is smaller than just the sum of the bounds. So we want to show that this is little o of n. And here we are given real or complex A and C. So of course the only way to get cancellation is what it is called. The only way to get it is by exploiting sign changes or changes in argument if you are dealing with complex numbers. So you want to understand the sign changes well enough that you're able to bound this sum by something better than the sum of absolute values. All right, so this often reduces to the case where you have an, f of n, e of g of n, and these have some special form. And so often f will be positive and this will capture the argument. So why do people put things in this special form? One reason is, as we have seen, terms of this form appear naturally in Fourier analysis. The other reason is that we just because we are human beings, we need to put things to reduce things to some special forms so that we can study those special forms and we can solve a finite number of problems and reduce other problems to them. It's just how humans organize knowledge. So what are some examples? So one example would be a character sum. So a character, I remind you, a multiplicative character is just a multiplicative map from the multiplicative group of z modulo pz to the complex numbers. So the sum here would be one of the simplest examples of a sum where you get cancellation is this complete sum. By a complete sum, I mean a sum over all elements of z modulo pz, or in this case, z modulo pz star. And this is what's called the Gauss sum. So, and Gauss, it's actually quite easy to show. Gauss showed that this is at least square root of p in absolute value. So, in general, in most sums, square root is the most you can hope for. As in this case, it's actually equal to square root of p in absolute value. In essence, well. In general, in most sums, with a few exceptions that we will see, reality is believed to be square root. You're very happy when you get square root. You cannot always get there. Another example will be an incomplete character sum. In this case, what do we know? This sort of thing, for n bigger than, say, p to the 1/2 plus epsilon, this reduces to Gauss sums. This is Pollo Vinogradov. For n in the range, say p to the 1/4 up to, say, p to the 1/2 plus epsilon, this is the remarkable result here, plus epsilon, the remarkable result of Burgess from the 50s, I believe. And then for n smaller than p to the 1/4, nobody knows how to give a non-trivial estimate here. Nobody knows how to show that this is little o of n. People haven't got square root cancellation here, no. But they do save a power, except when they get close to 1/4 plus epsilon. Well, in general, there are some not incomplete but complete sums, meaning sums over all elements of z modulo pz, for which we do get square root cancellation, thanks to deep results of Weil and Deligne. So, this board so far is mostly general culture, because we will actually work only with the last item. So this is a Klosterman sum, a complete Klosterman sum. So Klosterman gave the first non-trivial bound. It was something like p to the 3/4. So an inverse, of course, here means the inverse modulo p. This can be bounded by a constant times square root of p by Weil. So with more complicated multivariable sums, what you need to use is even deeper results by Deligne. Rather deep algebraic geometry. And lastly, what we will see today is rather sums that are on an interval, an arbitrary interval, of the form E of P of n, P a polynomial with at least one irrational coefficient. And it's very important not to confuse Weil and Weil. This is Weil with a Y, a completely different person. I have no idea whether the two are transliterated in the same way in Russian or not, but
Yes.
yes, that's a serious problem. well, one would be André Weil and the other one would be Hermann Weil, but different people. No, they did not fight, but they are distinct individuals.
The problem is that they have two books about number theory and algebraic number theory.
André Weil, yes.
And,
Analytic? No, it's
I don't remember, but
yeah, I don't know that one, but at any rate. Two important mathematicians, little confusion there, but I can imagine how, yes. But Davenport is only one Davenport. So this is already one reason. I mean, just the fact that it's one of several standard forms to which we can often reduce other problems, that of itself is a reason to study it. But another reason to study it, or to study other exponential sums, is equidistribution. So равно распределение, perhaps. Equidistribution. But before we translate equidistribution into Russian, let us make sure that we know what it means. So a sequence. So let me give you a definition. It's a definition that some of you will like and some will not like, but right after that I will prove that it's equivalent to a definition you might like better. So you have an infinite sequence. Say it could be on anything, but let us say that it's on the interval 0, 1, or in R modulo z, which is almost the same thing. This sequence is said to be equidistributed if the lim, so if whenever you have a continuous function f, the limit of the averages is equal to the integral. So people in dynamical systems like to call this the, well, time average, though here it's not really a time, you're just getting forward in the sequence, and this is the space average. And this is for what f? For any, so for every continuous f. So this is just the space of continuous function. Is that clear? Continuous complex valued functions. Very well. Why would we ever call this equidistributed? Well, let me prove that this is equivalent, first of all, to a criterion that we will use in analytic number theory, but also to something that is really intuitive in my view. So I do not know whether in Russian there's a standard way to state the following are equivalent. Strangely, in English people always write the following are equivalent. In French there is a very short form of that. So the sequence is equidistributed, that's one of the conditions. For any so this is what we would check in practice. So it's equivalent that the sequence be equidistributed in this definition, and that yes, that we find cancellation in this exponential sum. It's exactly that, showing that this. I mean, this is the same as saying that this is little o of n, whereas usually it's shorthand. And the third condition, and this I really like, but you can like whatever you wish. For any AB in the interval, the limit of the number, so the proportion of elements that will lie, the proportion of the elements that lie in the interval is precisely b minus a. It's precisely the length of the interval. So we say that a sequence is equidistributed if the proportion of elements of the sequence that lie in the first half is 1/2, if the proportion of things that lie in the first third or the second third or the third third is 1/3, and so on. And if you have a little interval of size 100, then the proportion of elements will be 100. And I like that definition, but as we will see, the first one is very natural from the point of view of ergodic theory, and the second one is very natural to check from the point of view of analytic number theory. Everybody with me? And what would be the Russian word for equidistribution then? Равнопределение?
Равномерное распределение. Да. Последовательность равномерно распределена на отрезке 0,1.
That's very long. We will have to write it somewhere at the end. So first, 1 implies 3. How are we going to do that? Well, we could just use the indicator function, 1ab, right? Except it's not continuous. But if it were continuous, we would be done already. But it may not be continuous. I mean, if it were continuous, we could just plug it into the definition, right? Because the integral of the indicator function is just b minus a. It's not continuous. However, you can approximate it very well by continuous functions. Yes? Yes.
Can we suggest to skip this part if everybody agrees?
Oh, because everybody knows it.
Yes, I think this.
All right. Okay. Well, so we say that we have been proven. So much the better. Excellent. All right. What is wise guys? What is an example of an equidistributed sequence? Do you want to give me an example of an equidistributed sequence?
Fraction part of arithmetic regression.
For example, so the degree 1. Yes. So alpha times j when alpha is irrational. So the proof would be, can you give me a proof? We can just use condition 2, right? Right? Because then you have j equals 1 m e mxj. Well, xj is just j alpha, so this is just, and this is of course just an arithmetic progression. This is about the only case in which you get more than square root cancellation, a geometric progression. So em alpha em and this of course is non-zero precisely because alpha is irrational. So you're happy, right? I mean, it's bounded by a constant, basically. No, wait. Yeah, it's bounded by a constant that depends on m, but that's fine. So of course it's little o of n. The rate depends on m and alpha, but that is fine. All right. So 2 questions. First of all, can we quantify this? It's very nice to say well, I don't care if it depends on m or alpha, it still obeys the definition of equidistribution. But can we say something about the dependence on alpha? Well, for that, the best way, I mean, here it is a baby case, but the best way is generally to approximate alpha by a rational number. So, just by Dirichlet, you can always, for any big Q, you can write things. Then m alpha is going to be at least 1 over 2q for all m up to q over 2. So this allows you to quantify the entire thing. I think Kronecker did a bit more than that. I think Dirichlet, I mean, here in Russia people say Dirichlet to mean just the basic pigeonhole principle, but that I think that was due to ancient pigeonholes in ancient pigeons in Babylon, and what Dirichlet's contribution was to use that to prove this. And then Kronecker proves I'd have to think of Kronecker. He was doing simultaneous approximation, I think, in higher dimensions. Yeah. It's the idea that Kronecker got when he was listening to an oratorio at one point. Never mind. There's an anecdote related to that. But what Kronecker proved was simultaneous approximation.
Yes.
That's right. But one alpha, that's Dirichlet. Very well. Yes. All right, and that, if you plug this in, this gives you some sort of measure of how well things are equidistributed. It gives you a notion of the size of this. All right, so, but we will leave, I will just make small remarks on how to quantify things. We'll focus more on the qualitative aspects here. So what about polynomials of higher degree? So alpha j is a very nice polynomial, but it has degree 1 on j. So what happens if the degree is higher than 1? Well, this is what I will show twice. So once using the proof due to Weil, see, I made that mistake too. And once using the proof due to Fürstenberg, the ergodic proof. Weil, I think, is from the very beginning of the 20th century. This proof, at least. And Fürstenberg's proof is from the end of the 70s. Not surprisingly, given that ergodic theory is a relatively young field still. Very well. So what about Pj mod 1, where the degree of P is higher than 1? So as we'll see, just like alpha before had to be irrational, here we need at least one of the coefficients of P to be irrational. And as we'll see, we can actually assume it's the first one, but, well, so So Weil's proof. So, wow, the proof of what? So, Weil. Let P. So I will prove just the qualitative statement, and I will make some comments about the quantitative part at the end. So I'm just going to say that there's a polynomial of degree k, and the leading coefficient, this alpha, is irrational. Then the limit, as n goes to infinity, of 1 over n plus n, e of Pn is 0. No? It depends on, so this is little o of alpha and k, it depends on alpha and k, but not on anything else. So what is the proof? The proof will be by induction. By induction on deck P. By the way, the ergodic proof also proceeds by induction, and it also uses the case of linear polynomials, which we just did, as the base case. So we need now to do the inductive case when the degree of P is k greater than 1. So what are we going to do? So when we don't know what to do in analytic number theory, we generally square. But here, this time surprisingly, we are not going to use Cauchy-Schwarz. Cauchy-Schwarz will just destroy the sign. Cauchy-Bunyakovsky, excuse me. We just expand. Right? And here comes the characteristic so right after this comes the step that is called Weil differencing. Because we're going to change variables. So one variable will be delta, which is a difference between n1 and m2. So this is, well, I wrote it this way, but I could just write a single inequality. So this just goes from m plus the max of minus delta comma 0 and very well. So, and why did he do this? Why did he change variables? This is just a change of variables, right? I mean, n is n2, n plus delta is n1, and the difference is no delta. That's just a change of variables. But why did he make the change of variables? It's because differentiation takes down the degree of a polynomial, and the same if you difference it, the degree goes down. This has degree. This is a polynomial on n of degree k minus 1. And delta k alpha is irrational because alpha was irrational and delta k are integers. So, but by assumption, by the inductive hypothesis, we have that for every epsilon, there exists a C0 such that well, E of this polynomial of degree k minus 1, this will be less than epsilon over square 2, say. It could be any other epsilon, n prime, for n prime bigger than C0. And so, can you still read this? So, for n, if n is bigger than, say, C over epsilon squared 2, which we can certainly assume, we have that, what? We have that, yes, this interval will be big enough, unless it's so small that the sum has to be small just for trivial reasons. E of P of n plus delta minus P of n epsilon is epsilon squared n. Thus, just summing over. So that's all we did. This is of degree k minus 1. So we have already proven the theorem for degree k minus 1. So we have cancellation. We just plug it in and we get, that's it. There's almost nothing to it. It's just an induction by degree. We reordered the terms, taking the difference, so the degree went down because that's what differencing, like differentiation, does. And then we have cancellation by assumption, and we put it in, and that was all. Yeah. If we want to get explicit bounds, we have to be a bit more careful. So this is the end of the proof, but let me just sketch how to get bounds. As usual, we write by Dirichlet. Then there are some minor difficulties. You see, you have to control, even if you know that Q is not very small, and if Q is very small, then you're not going to get much equidistribution. But even if you know that Q is not very small, you have to make sure that alpha delta K will not be close to something with small denominator very often. So that's what you have to take care of, but you can do it. So if you just go through the proof above carefully, I will not, but I will tell you some of the technical details, how to deal with them. You have that the bound that you get is of the following quality. So n would be the trivial bound. Here you have n 1 minus epsilon. And here, so this is a classical bound. Which is n to the 1 minus 1 over big K plus epsilon for Q in a range. Q not too small and not too big. It's the usual range. The Q bigger than some sort of thing going to infinity would be good enough to give you something non-trivial. But what is big K? The big K here, where K is exponentialized 2 to the K minus 1. So this is not so good, actually. So this is a power savings, a very good thing, but it's a savings by a small power, 1 over 2k, 1 over 2 to the k. So I should tell you here that this has been an important topic in analytic number theory, to improve this k, to make big K smaller. So in fact, yes, I would say the two main achievements are that of Vinogradov So I think it's from 1935, but he did some things later. And then there were many small improvements to Vinogradov, and then recently there was a big improvement by Woolley. He proved this with k equal to 2 little k minus 1. So he saves the log k. If you use smoothing, you can bring this further down, but as it is, this is close to optimal. And how they did this, I should just tell you. So this is an L infinity bound, right? You're showing that this is true for every alpha. What they did was show an LP bound and deduce an L infinity bound from that by showing that things did not change that rapidly. Well, so much for recent history. What are some technical details? Of the proof, not of Vinogradov or Woolley, but of Weil, excuse me, I myself get this wrong. So, as I said, we must control the size of the fractional part of this thing. And delta, you know, the deltas are variables. These are different deltas because you do this procedure many times. Well, but essentially, you can say, well, the number of solutions to this for any given m is not that large because it's essentially, it's a power of the number of divisors of m. So the number of ways to write, the number of ways of writing m as a product of 2k things is not that large. So exercise, I will give you the simplest case. So tau of m, the number of divisors of m, show that this is at most m to the epsilon. Not very hard. But then this means that instead, when you end up with these quantities that you don't know how to control, you're really having a sum over terms where you have, you're trying to bound something, and here you have m alpha, and then you have a sum here that gets bounded by 1 over m alpha. So, and 1 over m alpha, the trick is m alpha is small only very rarely, only for m congruent to -1, 0, or 1 modulo q. And this is not the only bound you can have, because you can also bound this trivially. Say, if this is of length about n, so this is bounded by the mean of this and n. So one time, or three times f of q, you give the trivial bound for the inside, and the rest of the times you bound it by 1 over m alpha. So that's how this sort of procedure is something that Vinogradov used very often, but I'm not sure how explicit Weil's bounds were, but I imagine he had some version of this procedure. Oh, and once you have that, well, you can basically use the fact everything. So you have the terms n, and then the rest you can bound by a geometric series, which is q log q plus n. Very well. By the way, somebody, when I write down, when people write down log in English nowadays, they always mean natural logarithm. ln is being phased out of existence. Nobody needs log to mean logarithm base 10, because nobody takes logarithms base 10 anymore. Except for computer scientists, because when computer scientists write 1, 0, they mean 2. But I know in Russia, I've been told recently that one should write ln.
No, you can write log.
It's understood that it's a natural logarithm. And you can say log, or one has to say logarithm. Well, we will discuss it when I'm drawing the boards. That's the good time for the discussion. All right. Now that we have discussed quantitative matters, a little qualitative note. So I hope that with these ideas, if you're truly interested in reducing this bound, you can sit down and do it yourselves. But the procedure is what I just gave, which is a proof for the qualitative statement. So a qualitative note. So the prop implies the equidistribution of Qn mod 1 for any polynomial with at least one irrational coefficient, not necessarily the leading one. So why? Well, see, if Q of x is, say, a over q x to the k, and then comes the irrational alpha, study each congruence class and congruent to b modulo q separately. And clearly, if every subsequence for n congruent to 1, 2, 3 modulo q is equidistributed, and that reduces because this becomes constant, then you are done. All right, so the classical approach is actually very, very simple, but many people also find the ergodic approach to be very elegant. It will take a bit longer, but it will give us the opportunity to introduce several key basic concepts in ergodic theory, which will be familiar to some of you, but hopefully not to all of you. Well, one should not hope that people don't know something, but we don't know everything, and it's always a good time to learn. So there will be one result actually that is important and that I will use and that I will state but I will not prove, namely the ergodic theorem that usually gets credited to Berghoff. It would take at least an hour, so I will not do that, and there are many standard proofs in literature. But everything else we will prove. Very well. So we're going to prove exactly what Weil proved, but with more abstract methods. So let us introduce some notation. So we will always work with a compact metric space here. So I'm almost tempted not to write down these conditions every time I have to write them. So maybe I should just refer to these as, well, little cross. So by M of x, we mean the space of probability measures. The space, well, the space with what topology? It will be the weak star topology. The terminology is clear. Weak star, let me briefly remind you what I mean. So the weak star topology. So first of all, this can be so the measures, so this is a subset of the sign measures on X. So the probability measures are the ones for which the measure is always non-negative and the total measure of the space is 1. The sign measures on X are the ones for which those two conditions are not necessarily true, and that can be identified with the space of with the dual space of the space of continued functions. So the linear functionals on. Well, whenever we have this sort of thing, something that is something star, then it acquires what's called the weak star topology. What is a weak star topology? Well, one way that I like to see it is that a sequence of measures converges, is said to converge to a given measure if and only if you have that the integrals of a function converges to the integral with respect to the mu for every continuous f. I think this is correct. Well, very well. So T induces a continuous map. So this is the definition of what it means for a sequence of measures to converge to a given measure. C induces a continuous map. Pull back. I always forget whether to put the star up or down, but in this context I think they mean the same thing. Что? T star from mx to mx. So it's a pullback of a measure. Well, really no, it's a push forward of the measure. Because if you have a measure here, it could work even if you had a map from x to y. If you have a measure on x and you want to induce a measure on y by means of your map, no, it's a pullback, yes, but back, forward, at any rate. You get the image. You want to impose a measure on y. What you do is you take, if somebody gives you a set in y, you pull it back, and then you take the measure here, and you say, oh, that's a measure. So you're pulling the set back and pushing the measure forward. Well, and for some reason the star has to be down. Yeah, always confusing. All right, and we will write. So it's for every Borel set. If somebody has forgotten what a Borel set is, do not worry. It's basically any set that is not pathological. Let's not go into definition. In particular, measurable, but well, let's forget about that. So MTX set of T invariant measures. All right, time to give some definitions. If I can find them. Why did I put the little one here? So if did I actually mean to be divisible? Did I actually mean to define uniquely ergodic before defining ergodic? I think I did mean to be divisible. That's very, very evil. All right, let me do that. So T is uniquely ergodic if MTX contains just one measure. So if this is just a set with one element, if there is only one T invariant measure. So theorem. Say I have a sequence of measures. Then any weak star limit of the sequence mu n, where what is mu n? Mu n is the average of the first n-1 push forwards so any limit point is a member of MTX. So why? Well, the proof will remind you, if you have seen it, the proof of the simplest ergodic theorem, that of Poincaré. So proof. So let us have, so say that we have a limit point, that is, there is a convergent subsequence with limit mu. Then for any continuous function f, we have that the difference between f with its transformation, mu and j, minus just f, mu and j. Well, I will just plug in the definition here. This is, well, 1 over nj. What? All right, I'm just plugging in the definition of mu and j here and there. Now that is, well, what does it mean to push forward a measure? It's the same as in the case of the function. I just need to compose it with t. Think about it for a second. So we have f This is clear. If I take just f dt star 3 lambda n, well, the integral of that is just the same as the integral of f composed with t cubed according to d mu n. All right. But this, well, it's like a telescope, right? Well, telescopes don't retract that much, but it's telescopic sum. So all the terms cancel except for the first one and the last one. And so this is at most 2nj and the L infinity norm, and this tends to 0 as j goes to infinity, because as j goes to infinity, n of j of course goes to infinity. So we have that estimate for every f in Cx, as we were proving. We have that ft d mu is equal to f d mu, because that's basically what quick star convergence means. You can put these things inside if it makes you feel more comfortable. And we have just seen precisely that this limit is 0. Okay, so this must be equal to that. But then this was just f dt star mu. But then it follows that, well, it's easy to see that continuous functions have as test functions. That is, if this is true for every continuous function f, then mu must be t invariant. Again, this could be its own separate lemma, but I will not bother you with that. All right. Okay, that's it. So mu is an empty x. Now, this implies immediately, and this is due to, I'm going to guess how this is spelled in Cyrillic. I'm going to guess that it is Krylov and Bogolyubov. Krylov. В? Krylov. Krylov Bogolyubov. Yep, it's just that there exists. So, MT, there exist T invariant measures. Why? Well, it's simply because there exists. Just take any old measure, and then there exists. So take there exist limit points. And you just apply the theorem. Why do limit points exist for any sequence in this space? Well, this is because, of course, mx is compact. Now, why is m of x compact? Well, you can see this as directly Tikhonov, which I am about to guess is spelled this way. Is it Tikhonov or Tikhonov? Like Tikhe. Tikhonov, Bia, if you prefer, Vanach Alaoglu. Yes. The point is that, as I said, m of x can be identified with a bounded subset of Cx, and x is compact. So if you have a bounded subset of, yeah, all right. Yes, the standard theorem in functional analysis. Well, as I said, I was being very perverse because I defined uniquely ergodic before defining ergodic. Now let me define ergodic. So, well, let's write a little cross, namely x, just remind you for the last time, x compact metric, t continuous. And mu t invariant. So we say that mu is ergodic with respect to t, or the contrary, or the other way around, that t is ergodic with respect to mu. They mean the same thing. If for every measurable E that is invariant, so every invariant subset must have either zero measure or full measure. Well, one, since we are dealing with probability measures. That's the definition. So every invariant subset must be either tiny or enormous. Now what? Why do I always
Maybe some connect.
excuse me? Yeah. Maybe some what?
Если вот неэргодично.
So what is the connection between uniquely ergodic and ergodic? That's I will explain that in a second. Or no, something else?
Is the X connected? No.
T is continuous. Yeah, if you had something, yeah, well, this has to be in some intuitive way. No, I don't need to add connected, but it is in some intuitive way. It may resemble the definition of connected, but it is about measure. It's not about openness and closure.
Okay.
Yeah. There may be invariant subsets. It's just that they will be either tiny or enormous. All right. So lemma. So why do I say so? Condition plus. If mu is an extreme point of MT, meaning not a linear combination of two other measures, then mu is ergodic. This is what we will prove, but I will just note that the converse is also true. Ergodic measures are extreme points. So proof. And this, by the way, tells you why uniquely ergodic is called that way. So if you're uniquely ergodic, then you have only one point, which and by definition that point is an extreme point of the set containing just that point. So there will be an ergodic measure, just the one. But conversely, if there is more than one point in MT of X, there will be more than one extreme point, so more than one ergodic measure. So proof. Let mu be non-ergodic. Then by definition, let B measurable be such that, well, there will be some invariant B with measure between 0 and 1, strictly between 0 and 1. But then we can decompose mu as a linear combination of two measures. How? Well, just a measure restricted. Wait, what did I do here? Yeah, it's times. So measure restricted to B and the measure restricted to X minus B. It's just almost a tautology. Scale down, of course, so they are still probability measures. So the measure of X minus B is, of course, 1 minus the measure of B. That's it. It's very simple. So the corollary would be that in general, again, for X compact T continuous, ergodic measures exist. Why? Because extremal points exist. Actually, that's actually a non-trivial fact, or it's referred to as a non-trivial fact. In full generality, it's a theorem of Crane and Millman, and I'm going to guess that it's also written in Cyrillic, probably. Otherwise it would be Crane, or maybe it's not, but who cares? At any rate, so what would be, let me see, another thing. At least I'm pretty sure Crane is written in Cyrillic. Otherwise it would be Crane. Compact. Little star. If T is uniquely ergodic, then for every continuous in fact, I'm going to write it down formally, but it just means that the sequence of T and X is equidistributed, because that's what equidistribution means, as we saw. So here you see the deep connection between equidistribution and unique ergodicity. This is for every f, and I think for every x. Yes. Yes. Literally for every x, not just for almost all x. So a proof. Let mu be the only element of mx t, because the base is uniquely ergodic, so there's only one. So we apply theorem 1, did I call it? I think I called it theorem 1 to the constancy, the one where we had the limit points. Was it theorem 1? You know, when you had some measures, and I said every weak star limit point is a limit. So delta x is just the point mass at x. We obtain only one limit point yes, because, well, every limit point by the theorem is going to be in MTX, but there's only one of them. Right? Yep, namely. So every limit point is going to be that, so a sequence actually has a limit, namely mu. And so this delta t and x, which is nothing other than the pullbacks dx, right? This tends to 0. This tends to mu. And that's it. Nothing else. It converges to mu because it cannot converge to anything else. Yeah. So, well, I should have put this in the statement, perhaps. All right, so we say in general, we say that x is generic if the sequence is equidistributed. So as I emphasize, this is going to be true for every x, because it's actually not so special for this to be true for most x. In fact, as we are about to see, that always happens. So for almost all x, a sequence like this is going to be equidistributed, almost in the sense of the measure. How do you prove that? Well, this is a one theorem I will not prove here.
I'm sorry.
Yes.
This definition is with respect to some measure.
Yes, that's right. With a measure that, with respect to a measure mu, some measure mu. It's not necessarily this case of we have finished the proof. So mu is some measure. You're talking about the general case. So this means that if we are uniquely ergodic, then every point is generic. Of course, generic generally denotes a property that is true almost everywhere. And we're about to say that this is the case in general. So here's the ergodic theorem. There are several. This is the one that is usually ascribed to Birkhoff. There is some controversy about the right name. I don't know what it's called here, because Birkhoff did state it, but not in the fully general form. Also, it said that Birkhoff was an ass, but and that may be the real reason why people don't like the name, but let us not go into that. And it's a different Birkhoff from the other Birkhoff. They're actually father and son, but never mind that. So, so if you just take an L1 function, this is telling you, then this average converges almost everywhere, that is, for all x in a set of measure 1 with respect to mu, of course. And moreover, this f mu, this f star has the same integral of f d mu. Yeah. This is almost a postscriptum. If it is if t is ergodic, f star of x is just so. F star of x is a constant. Well, but this is easy, because f star has to be t invariant, that much is clear. So f star is a constant. And if it's a constant, this integral is the same as that of f, then it has to be equal to the integral. We are in the space of measure 1. All right, we will not give the proof, as I said. It will take us too long. It is standard. It's quite nice, but a bit long, and you're encouraged to read it. It's not that long. For example, one of the many places where you can find it is in proposition 2.30 in Einsiedler word. And an easy corollary is that, well, with the usual, so X compact metric T continuous and mu T invariant and ergodic, then almost every point is generic, what I was saying before. This, every x in a set of measure 1 is generic. So what's special here then in unique ergodicity is that for every point x the sequence is equidistributed, because what we are about to show as a corollary to this is that for mu an arbitrary ergodic measure, not necessarily uniquely you don't need the unique ergodicity to prove that equidistribution is the case for almost every x, almost every reservation to the measure. So the proof of the corollary would be, well, I will sketch it. So let f of n, fn be a dense sequence. It's easy to see that it exists, or because x is compact. So dense with respect to the infinity norm. So we apply the ergodic theorem to each fn. So for each fn, we get a big fat set x prime or x prime n on which things are fine. But the intersection of a countable number of sets of measure 1 has measure 1. Taking intersections, we obtain x prime x, mu of x prime equal to 1, such that the limit, such that the point is generic for every so the ergodic theorem shows not that it shows that for a given function this converges for almost every x. But here what we do is, well, we want all functions basically, but all we will have to do is build some sort of net there. Because the thing is compact, we can. And so this is equal to, for all and so, well, I will leave the details of the rest to you, but they are really trivial. For every continuous f, we find f of I closing the L infinity norm, and well, just to meet the last line of the proof. So it's you have to find an fi very close to it, so it must be almost fine up to epsilon, but for epsilon is arbitrary, so you're done. All right. So enough preliminaries. Now let us go to the work of Furstenberg. So what did Furstenberg do? So the main step, I call this proposition, but it's really the core of what Furstenberg did. So this will work as some sort of inductive step, because it shows, starting from something uniquely ergodic, he will build a transformation that is uniquely ergodic. He will show that some bigger transformation, some more complicated transformation is also uniquely ergodic. So he says, let X be, as usual, compact metric. This is what happens when the mathematicians get lazy. So this is uniquely ergodic. Mu is the only invariant measure, since this is ergodic, this is uniquely ergodic. Now G will be a compact group. Now, a compact group, it will have a single right and left invariant measure, the Haar measure. It's left and right invariant with respect to multiplication. And you have a continuous map, xg. A continuous map C from x to g. And we define, as I said, a more complex. So we define, if it's too low for you to read, please tell me. It's too low for me to write, but so we define. So a transformation from y to itself, where what is y? Y is just x cross g, and we define the transformation by sxg equals, so in the first coordinate it will just isolate t, and in the second coordinate x will be acting on g. So it's some sort of cross product, if you wish. And then what are we going to conclude about that cross product of sorts? We're going to conclude that, well, so t here is uniquely ergodic, and we want to show that s is uniquely ergodic. And what we'll show is that if s is ergodic, then it is uniquely ergodic. Proof. Oh, let me write down the conclusion. I didn't finish because there wasn't enough space on the board. So if S is ergodic with respect to mu cross mg, it is uniquely ergodic. So this would enable us to construct bigger and bigger, more and more complex uniquely ergodic transformations, starting from smaller ones. So proof. So first of all, this is invariant under S. It's the first thing to check, of course. So for f, a continuous function, we have ft star mu mg by Fubini, we can just split into an integral over x and integral over g. dg dx, where this has to measure mgg, this has to measure mu. But the Haar measure is invariant on both sides. So in this case, we will use the left invariance of the Haar measure. dg dx, and now we use the invariance of mu under t. And now we use Fubini back again to put it back together. This is the integral of f with respect to the mu cross g. All right. Very well. That was the routine part at the beginning. Now comes the interesting part. So we assume that S is ergodic, right? Let E be the set of generic points. We want to show that it is the entire scene. We already know that by the corollary to Berkhoff, that mu of is equal to 1. So it has full measure. We just want to show that it's entire set. Note first of all that the set is invariant under right multiplication. Why is that? It's simply because the higher measure is invariant, as I said, not just by multiplication on the left, but by multiplication on the right. So let me do this in full. So what am I doing here? I'm just multiplying. No, here I'm just using definition of fh. And here, it is here that I use the fact that the measure is invariant on the right. So it's just the integral with respect to the mu mg. Because I should change mg by shifting mg. As in, it no longer shifts this, it should shift the measure, but the measure is invariant. So this means that if you have a point that is, for which this works, if you have this one, if you have a point which, well, if you have, well, all right, this does show that it shows it in the other direction, but obviously you can invert. So if you have a point that is generic, then if you multiply the point on the right by h, it's still generic. That's what we wanted to show. So that forces it to be of the form E1 cross G for some E1 of full measure. Now, consider the projection from y, which is x cross y, g, of course, to x. Then, mu, the push forward of nu to x is t invariant. That's just because the projection, the transformation is defined in this way. That's what it does to the first component. That's t. So if I project it to the first thing, you get that it's t invariant. But if there's only one t invariant measure by unique ergodicity in x. Mu star v equals mu. Hence, nu of e is equal to nu of E1 cross G is equal to mu of E1 is equal to 1. Very well. Yes. Simply because nu of E cross G will be nu push forward by t e1, but that, as I just said, is mu. But mu of e1, as I said, is 1. So everything is fine so far. But we also know by the corollary to Birkhoff.
Sorry.
Yes.
Where is the first moment when we met the measure mu?
That's precisely what I'm thinking about. That's what, where did we define mu? So does this mean? Wait. That's what I'm wondering about. Oh, I think yes. I think we introduce it right here. So nu is just any measure, and we want to show that it has to be.
It's S invariant measure.
Wait. Yeah, we want to show that nu is an S-invariant measure. We want to show that it is precisely mu cross mg. So.
And the generic points, the set E, the set of generic points.
With respect to mu mg, as I said, yes. All right. Very well. So we're trying to analyze this measure nu. We're trying to see what it looks like. So we know that its push forward has to be mu by unique ergodicity. So nu of E1 by what we just proved before has to be nu of E, which is of the form U1 cross G, must have measure 1, simply because it's a measure of mu. All right. So what now? So with the corollary to Birkhoff, nu almost every point is generic with respect to mu. Hence, there is, since E has measure 1, well, some of these almost every points have to lie in E. There is a point, simply because all the other points, ones that are not in E, have measure 0. And nu almost every point means a set of measure 1. Generic with respect. But if a point is generic with respect to one measure and generic with respect to the other, that forces the two measures to be the same, because it forces the integral of every function to be the same with respect to them two measures. Magic. It must be the same.
Yeah, but where we have used the organicity of S.
Let me see. We used it because, yes, we used it in order to get the stronger form of Birkhoff. Remember, the corollary to Birkhoff was for so Birkhoff told us that there were these sequences that converge, and he tells us that if the measure is ergodic, then the limit is actually a constant function. And then when we were proving, let me see, the corollary to ergodic measure, yes, the corollary where we say that almost every point is generic. So here we use the ergodicity of S. Yeah. Yes, here it's because here it's because nu is ergodic. Here we're using the ergodicity of nu. So I think here we should assume then that nu is ergodic, but it's fine. This is fine, because if you have only one ergodic measure, then you are uniquely ergodic, because the ergodic a set that would have more than one element would have more than one limit, one extremal point. But where did we use? Yes, and here did we use the ergodic? Yes. Of mu cross imaging. And see, so that an ergodic. Yes. Here we're really using the fact that a convex set with so deep down, well, a convex set with more than one point has more than one extremal point. Because we just showed that every ergodic measure must be equal to the one measure, but that implies by this that every t-invariant measure is. All right. Well, what now? Yep. All right. So a corollary now. So let alpha be rational. S a transformation of the so T here will just be R modulo S. And this transformation is defined by x1, x2 up to xk gets mapped to x1 plus alpha, x2 plus x1, xk plus xk minus 1. This is uniquely ergodic. This will be a consequence of the theorem above. So proof. So S is just built as in the last theorem by this cross product. So by that theorem, by the theorem of Furstenberg that we just showed, enough to show S is ergodic with respect to the Lebesgue measure. All right. We know already, by the way, this requires some input, right? Well, the case k equals 1, we know this. We already proved back before we knew back before we knew what uniquely ergodic meant, we proved that for k equals 1 this is true. Because for k equals 1, this is just a shift by alpha. This is just telling us that adding alpha, if you consider just a linear polynomial x constant, x is a constant here, plus alpha j, that is equidistributed for every constant. So we know this for k equals 1. Let us do it in general. We will not actually need a base case and induction, I'm just saying that we already know this. So let f be null to k, S invariant. So because it's an L2, we can write a Fourier expansion without any problems. So let fx be written as a Fourier series, multidimensional one. So this is the dot product between x and n. And now what we're going to do Well, because f is invariant, we're going to be able to compare the f of x is going to be the same as f of s of x, and we're going to be able to compare the coefficients. So it will just be that sort of game, and we will be done quite quickly. We will be able to show that f has to be constant, and that will show that the measure is ergodic. So not a big deal. And then we will be done with this corollary. And once we have this corollary, you will see how the theorem on equidistribution of polynomial values will pop out quite easily. Now, f of sx, this is of course Cn e to pi I n sx, but I can just rewrite this slightly as follows. Cn, so it's just a very quick calculation to check that this can be rewritten in this fashion. Well, what is S prime nx? So S prime is now linear transformation applied to n, no longer to x as S is. So S takes n1, n2 up to nk to n1 plus n2, n2 plus n3, nk minus 1 plus nk, nk from zk to zk. Since fsx equals f of x, Cn and so Cn equals C. You can just we can just compare coefficients because f is as invariant. The coefficients must correspond, right? But the coefficient here, let me see. Yes, the coefficient here for f of x would just be Csn, Cs prime n, right? So f of x, we can just reorder the terms, and we get Cs prime n e to pi I s prime n. So we have that this coefficient must be equal to this one. This is what I'm writing. In particular, this and s prime. In particular, their moduli are the same. So for each, now we are going to show that this is going to lead us to an interesting place, because for each n, either these things are all distinct, but if they are all distinct, then there's an infinite number of repetitions of this thing, and then the L2 norm would not be bounded, but it is bounded because this thing is in L2. So this would imply that Cn has to be 0, or C prime. So we have, so for some P, so for Q1 and Q2, you must have that the things repeat each other. But then what happens? Well, just look at how S prime is built up. You would need, here you would get nk minus 1 plus q1 nk, and in the other case you would get nk minus 1 plus q2 nk. So the only way the two things would be the same is if nk is 0. But then you do the same thing again, and you get that nk minus 1 is 0, and so on and so on. So only the only case remains is n equal to n0, 0, 0. Then Cn, what you get is that Cn is e2 pi I n1 alpha Cn. This just becomes a fixed point. n0, 0, 0 is a fixed point for S prime, that much is clear. And so either Cn equals 0 or n1 equals 0. And so n equals 0. Hence, f is constant. You see, the only coefficient that can fail to vanish is a coefficient for the vector 0. So we have shown that the only S-invariant function is a constant function. S-invariant constant the only continuous function that is invariant is a constant function, and so S is ergodic. S is ergodic, and so we are done. The corollary is proven. Now, in the non-existent time that remains, let me just prove the second consequence. And I'm tempted to just give the reference, but let us actually do it. It's trivial. So, proof of Weyl equidistribution. So, Pj mod 1 by Fürstenberg. So, what did he do? Well, just rewrite S. View S as a transformation, not of tk to tk, as a map. Point is tk to a point times tk. Well, the same thing. But just rewrite in the following way. So you have this diagonal matrix, zeros otherwise. Here you have x1 up to xk. Here you have x1 plus alpha, x2 plus x1, up to xk plus xk minus 1. So this tells you what sk is, because an sk is going to be just this matrix to the n, alpha 1, x1, up to xk. But this matrix to the n, with all the ones in the diagonal and the ones under it, this is just given by 1, n1, n choose 2, n1, and so on, up to nk, n1. And so this tells you that the last entry in the vectors, so this is going to be alpha, and then many things, and the last one is going to be nk alpha plus nk minus 1, xk minus 1. So, and we're just taking, let me change the notation slightly, we will take this to be, so p of x is ak, x to the k, ak we can take to be rational, plus ak minus 1, xk minus 1. So what do we do now? We can just pick, but here we're, this is up to this x1. Yes. So we can choose, remember that we're proving things that were true for every point. For every point, the orbit was equidistributed. That is what unique ergodicity implied. But then we can choose x1 up to xk, so our point, to be such that this polynomial is the polynomial on n with these coefficients. So alpha is going to be k factorial ak, and yep, p of n is going to be n k alpha. That's always possible. So what you are going to have is that by the other corollary, because the measure is uniquely ergodic, you have that the orbit of x under S is equidistributed, but that means in particular that it's the projection of its last item, the projection to the last copy of T, must be equidistributed as well. So this P of n is a projection on the last coordinate of S and x prime is equidistributed on T. Ta-ta! That is the end of the proof. And you see, well, it took us some time, but it was in part because we had to introduce a lot of interesting material that ends up being a very good base, not just in number theory, but elsewhere. So I think it's a very nice application. It looks less elegant simply because we had to get our hands very dirty, but in fact, it was more abstract than what Weil did. So it has its advantages and disadvantages. In practice, Weil gives better bounds, and the people who came after Weil worked very hard to give even better bounds. But this has a certain elegance, and this also was one of the first examples for how useful ergodic tools can be in equidistribution and in other statements lying between analytic number theory and additive combinatorics.